Right, so on Thursday we did a rate law problem. Rate law. So one of those types of problems will be on the exam. We'll go over another one before the actual exam for our test review. So just be aware of that and do that practice homework problem, do the practice quiz problem, and I think you should be okay. And now we're stepping into something that's a little bit different but related to the rate law, and that is this sheet here. So first thing I want to tell you guys is bring this to the exam. Okay? So bring to exam or test 2.
Can we always like draw it out, like we can't print it out, like really draw this out like on a piece of note paper possible?
You can. I think I should have extra copies. If I don't have extra copies, you can draw it out. Yeah. All right, so this is for the reaction A goes to B. Okay, reactant A goes to product B. Okay, so what did we mention the rate law of this is going to be? Okay. The rate law of this is going to be how fast A goes to B is going to equal to some rate constant K, lowercase k, times the starting material of A, initial concentration of A, how much you start off with. And that A is raised to some power, I'll call it lowercase a. Okay, lowercase a. All right, our job in the rate law problem, which we did last week, was to determine K, which has, unique units. It has very unique units, and to determine this exponent. So do we remember how this graph looks like? Okay, if I were to plot over time on the x-axis and the concentration on the y-axis, what would A look like? What would the profile of A look like? It'll go down, because as A goes down, what begins to appear? Concentration of A goes down. Over time, what happens to B? It goes up. Okay. So as A goes to B, the concentration of A will go down, the concentration of B will go up. The rate of disappearance of A should equal, because it's a 1-to-1 ratio, the rate of disappearance of A should equal to the rate of appearance of B. Okay, appearance of B. So how fast does this reaction occur? A goes to B. We measure that with decay. Okay, remember the term decay? This is how we will determine how fast A goes to B. This is how we will determine how fast the reaction is going to proceed. Okay, not by B appearance, but by A decay, A disappearance. So this is all about the decay. Decay of A. So this decay of A is symbolized by this exponent A. Okay, this is called the order of decay with respect to reactant A. There's only one reactant. If there's 2 reactants, there's going to be 2 orders. Okay, 3 reactants, 3 orders with respect to that individual reactant. So I'm going to call this exponent A the order of decay with respect to reactant A. With respect to reactant A. So this A can be 0 order. Let's say A is equal to 0. This will be 0 order decay, or 0th. Okay, if A, I don't know what that word is, 0th. We had a discussion. Is this 0th is a word or not? All right, back to the lecture. If A is equal to 0, if A is equal to 0, this exponent, what is something raised to the power of 0? 1. So if A is equal to 0, rate is going to equal to K. Okay. So this is zero order decay. Okay. So rate is equal to K. If A is going to decay with zero order kinetics. And so if we plot concentration over time, if A decays with zero order, it's not going to look like this, but it's going to look like a straight line, okay? And straight lines, I'd like to convince you, are nice because it's a nice formula. Y equals mx plus b. Okay, so we can analyze this really nicely because it's a straight line. Okay? Y equals mx plus b. So this is the equation. So this is what you need to know, but you bring this to the exam. Okay? The concentration of A at some time t is going to equal to the initial concentration A naught minus KT. All right? So for zero order, okay, if that reactant is going to decay with zero order, and our reaction is A goes to B, okay, if reactant A decays with zero order decay, then the equation is concentration of A at some time t is equal to A naught minus KT. Okay, so this is the equation you want to plug and play for the exam, but you can bring this. You don't have to memorize it.
So that's this formula of like the A to like this zero power. We don't have to memorize that.
Well, you have to find A is zero. If A is equal to zero, if this exponent is equal to zero, this is the equation you'll use.
Oh, so to me we don't need to memorize the equation will provide.
You'll need these equations you can use by taking this sheet to the test.
Okay.
Okay. All right, so what is A at some time t? That's A at some time t. Okay. What is A naught? Okay, A naught is the initial concentration of A. Okay, starting amount. Okay, this is the starting amount. Okay, and what is lowercase t? It's not temperature. What is it? Time. Okay. So which would be bigger, A naught or AT? Which is bigger? Okay, A naught will be bigger. Okay, why is A naught bigger? Because how fast the reaction is going, we're going to measure it by what? By the decay. Okay, so A naught is going to decay. So after 5 minutes, how much is left over? After 10 minutes, after 12 minutes, after an hour. Okay, what is AT? T is time. So this is the equation you want to use on the test. You can have this sheet on the exam. Okay? So concentration over time, it's a nice straight line. Okay, the slope is equal to minus K, so you just get the slope and get minus K, which is good. So if the rate is equal to K, zero order decay for the reactant, if we double the starting amount of A, how much does the reaction go? How fast does it go? It stays the same. If we triple the starting amount of A, how fast does the reaction go? The same. Okay. If we quadruple the initial amount, starting amount of A, how much does the reaction go? Okay, the same. Right, that is for zero order decay. Zero order decay. All right, and now we have another term here called half-life. Okay, what is the half-life? If that reactant is going to decay with zero order, okay, it's this equation. Okay, again, you can bring this sheet to the exam. Okay, what is the definition of a half-life? All right, so the definition of a half-life is a time. Okay, what is time? What are units of time? seconds, minutes, hours, days, years. For something like, I don't know, plutonium or some of these radioactive wastes, it could be years. I think they have difficulty disposing uranium because it has half-lives in centuries. So how many of you have heard the term half-life? Okay, particularly in the radioactive area, nuclear chemistry. So half-life, I want you guys to know, is a time. Okay. Seconds, hours, minutes. Okay. I think half-lives of certain drugs that we take in our body have half-lives of minutes, or maybe hours, or maybe days. Okay, it depends on the drug. But it's a time. Seconds, minutes, hours, days, years. If it's something like uranium, it could be centuries. But it's a time in which 50% of the molecule of the substance is gone, decays. When I say 50% of the substance is gone, that time in which 50% is gone or decayed, it could be, if it's a drug, it could be absorbed in the body. If it's, radioactivity, it could be emitted as some type of particles. Okay, so some sort of decay where it's gone. So a time in which 50% is gone. Okay? Seconds, minutes, hours, days, years. So on an exam, I'll ask calculate the half-life, and students put, I don't know, they'll put like millimeters or mercury, or they'll put degrees C or Kelvin, or a molar over seconds. Okay, and why is that wrong? The units are wrong. Why? It's not a time, okay? It's not a time. So what's the equation for a half-life if that substance decays with zero-order kinetics? It's this, okay? And this is the equation you'll use. All right, and this is the profile, okay? This is the profile over time. Okay, what are the units of K rate constant? Okay, the units of K rate constant are molar over seconds, because remember, this rate constant has different units. And this is for the reaction A goes to B, remember. Okay. Different reactions will have different rate constants. All right, so that is if that reactant decays with zero-order kinetics. Okay, T1/2 is the initial concentration divided by 2 times the rate constant. All right, let's do our second scenario. Let's say A decays with first-order kinetics. Let's say A decays with first-order kinetics. This exponent A is equal to 1. Okay, if this exponent A is equal to 1, what will that be? What will that make this rate law? Okay, what is anything to the power of 1? It's the same thing, right? Okay, A to the power of 1 is A. So rate is equal to Ka. Okay, that's what we see here. Okay, why are these negative? Of all things, why is it negative change in A over time? Why is it negative change in concentration of A over time? Why is this negative? Why is it negative here too? Because it's a decay, it's a reactant, it's a decay, correct. Okay. So if this A reactant decays with first order kinetics, it's going to look like how we talked about, or how the book talks about it. It's going to kind of look like this. Okay, so the problem is that this is hard to analyze mathematically. So what do? You do what's called in math a transform. Okay, transform. You do a linear transform. And the way you do a linear transform, so this is called a linear transform, You got to somehow convert this to a line. Y equals mx plus b. You have to somehow convert this to a line. Okay, how will we convert this to a line? Okay, instead of plotting concentration over time, we will take the natural log of each concentration. Okay, we'll take the natural log. Okay, so plotting the natural log of the concentration, not the concentration, the natural log of each concentration over time, we get a nice straight line. Okay? And a nice straight line is nice because it's just simply y equals mx plus b with the slope equal to minus k. So we're plotting the natural log of concentration over time. So this is the equation we're going to use. Okay, so this is what you want to use for the exam. Okay, natural log of A equals natural log of A naught minus KT. All right, so let's go back here. Again, you don't have to memorize this. Just make sure you know what to use for the exam. So 1, if our exponent is equal to 1, this is first order decay. And the decay is going to follow this equation. Okay, A naught is what? Initial. Okay, minus KT. So this is what we want to don't memorize. Bring this to the test. All right, so what happens if we take a first order decay what happens if we take a first order decay and double it? Okay, what happens to the reaction rate? Okay, it too doubles. What happens if we take the initial reactant A and triple it 3 times the starting material? What happens? It jumps 3 times. What happens if we quadruple it? Okay, the reaction rate will also quadruple. Okay, so that is first order. Okay, this is the equation for the half-life, 0.693 over K.
So wait, why are you jumping from 1 to 2 and then from 1 to 3? What does that mean again?
If I double the concentration of A, how fast will the reaction go? Twice as fast. If I triple the concentration of A, how fast will the reaction go? Triple as fast. If I quadruple A...
Oh, so it's proportional, so it's like, so the...
Yes, it's proportional.
Okay.
But this, in zero order, is not proportional.
Oh, and so in zero order, it always remains 1, essentially.
Yes. Because your rate is K. Your rate here is not dependent on your starting amount. Here, your rate is dependent on your starting amount. See? Rate is dependent on concentration of A. Here, the rate for zero order is just, doesn't depend on it, it's just K. All right, so this is the half-life, 0.693 over K. So another thing, just want to bring your attention, 0.693 is also natural log of 2. Natural log of 2 over K. There's a student last semester who said, I don't understand, natural log of 2.693, what is it? And, I had to convey to her that it's one and the same. Okay. Natural log of 2 over K is the same thing as 0.693 over K. And the units for this is 1 over seconds. Again, want to reiterate the reaction for this sheet here is A going to B. All right. So we did a zero order decay for that reactant. If that reactant decays with first order decay, this is the equation you'll use. And now finally, what happens if A is equal to 2? Okay, let's plug in 2 here. Okay, so the rate is going to equal to your rate constant K times the initial amount starting material of A. Okay, if that decays with second order kinetics, second order decay, this is what it will look like. And this is what our rate law will look like. Okay? Unfortunately, we have another issue. Okay, concentration over time is kind of like how we projected it to be. Okay, so it's hard to analyze this unless we do in math what's called a linear transform. Okay, so how can we convert it to a straight line, which is y equals mx plus b? Okay, we'll do a linear transform. Instead of plotting concentration over time, what can we plot? Not natural log, but the reciprocal 1 over. Yes, that's correct. Okay, so this is another linear transform. Okay, this is something that's used in math a lot. Okay, we'll do a linear transform. And the slope here is k. Okay? The slope is equal to k. But wait a minute, how do we get this to form a line? Y equals mx plus b. What do we need to do? Not concentration over time, but I think somebody said it. What do we plot? What is it that we plot? Okay, we plot 1 over. Okay, 1 over concentration over time. All right, so this gives us a straight line. And this is the equation for a second order decay. All right, second order decay. 1 over A equals 1 over A naught plus KT. All right, so let's finish up this table here. If A decays with second order kinetics, the equation you'll use is 1 over A at some time t is equal to initial concentration A naught plus KT.
So wait, so in terms of the equation, so it's 1 over the capital A brackets t equals 1 over A to 0 plus
A naught,
naught.
A at time t, A naught, which is initial, yes,
Okay.
plus rate constant K times t time. That is for what type of decay,
For
Bailey?
the, second order.
If that exponent is 2, this is the equation you'll use, okay,
Okay.
for the decay. After 5 minutes, how much of this is gone? Okay, this gives us an insight into how fast a reaction occurs. See, the idea is decay is not decay is not decay. Okay, it doesn't just decay. Oh, it just decays. Okay, it can decay either this way, 0 order. It can decay this way, first order, in which case we'll know because we plot natural log of concentration over time and get a straight line. Or it can decay this way, second order, in which case we plot 1 over concentration over time and get a straight line. Okay? So decay isn't just decay, is not just decay. That's the basis for all the, even drugs that you take. Okay, if you ever read like a prescription drug, they have this little sheet, and you read the fine print, it will give you the half-life, like, Synthroid or whatever medicine you're taking, Tylenol. Okay, you can look it up, all the half-lives. Well, it really depends on how that molecule gets absorbed in the body. Okay, 0 order, first order, second order. Even though this is beyond the scope of the class, when a hormone binds to a receptor, it can also be 0 order, first order, second order. Okay, when glucose binds to its receptor, its kinetics is kind of modeled after 0 order, first order, second order. So actually, you know this when you go to your higher classes. I'd like to convince you that this becomes more important later on. Pharmacology, pharmacokinetics, okay, all that stuff. All the PA students will know this, or PA program students, or the physiologists. All right, anyways, back to this. All right, so rate is equal to K. Okay, A we mentioned is equal to 2. All right, what happens if you double A? Starting amount A. What happens to the reaction rate? It goes up by how many times? 4, okay? What happens if you triple A? How fast will the reaction go? 9 times. What happens if you quadruple starting amount of A? How fast will it go? 16 times. Very good. Okay, 16 times.
So wait, so then what's the ratio from 4 to 9 then? I'm a little confused on that.
No, if you triple the quadruple the concentration of A, this will go 16 times as fast.
Oh.
4 squared is 16. All right, and here is the formula for the half-life for a second order. Okay, 1 over K times A naught. Yeah, 1 over K times A naught. All right, and finally, the units of K are m to the minus 1 seconds to the minus 1. Okay. All right, just a word on these units. Okay, again, this is for the reaction A goes to B. Okay, a word on these units. M over seconds is the same thing as m times seconds to the minus 1. Same thing. This and this are the same. Okay, 1 over seconds is the same thing as seconds to the minus 1. This and this are the same thing. And then finally, m to the minus 1, seconds to the minus 1. Okay, I can move it down. It's the same thing as 1 over m times seconds. Okay, same thing. Same thing. All right, so either this can decay for this class 0, first, or second order. All right, these are the equations you'll use. These are the equations you'll use. Okay, bring this to the exam. You do not have to memorize them. It's just a matter of plug and play. All right, plug and play. Plug and chug or plug and play. All right. Any questions or comments? Okay, let's go ahead and do some practice problems involving this. Involving these 0, first, and second order. Okay, we'll do that now. And let's go to page 10 of our notes. All right, the reaction 2A goes to B is first order. Okay, let's highlight this first order. With respect to A, with a rate constant of 2.8 times 10 inverse seconds. 2.8 times 10 inverse seconds. We're going to call this 28 over seconds. Okay, at 80 degrees C. Okay, change the temperature, change the rate constant K. Okay, how long in seconds? How long? What are we trying to solve for here?
In seconds.
Time. Yes, in seconds. Very good. Will it take for A to decrease? Okay, what does decrease mean to you guys? Okay, it means decay. To decrease from 0.888 molar to 0.14 molar. All right, so what equation shall we use here? Okay, which equation? 0 first, yes, first order. So I'm going to use this, Antoinette. Okay, taken from our sheet that you can bring to the test. natural log of A, I'm sorry, not concentration of A at some time t equals initial concentration A naught, this, oh, sorry. Okay, first order. Okay. I'm picking the wrong equation. First order. Okay, first order. Natural log of A equals natural log of A naught minus KT. All right, so what is A naught here initially? Okay, don't put units inside the natural log. Okay, don't put units inside the natural log. So this is initially. And then what is the final concentration? 0.14, very good. Okay, minus K. What is K? 0.8 over seconds times T. Okay. All right, are you okay with this plug and play? Plug it in and chug it out, get it out. Okay, this equation, make sure you pick the right equation. Notice I almost picked the wrong equation. Okay, this is not zero order. What order is it? First order. Okay. And do we know how to do this on our calculator? All right, so I will isolate T here. I'm going to take divided by minus the 28 over seconds. Minus the 28 over seconds. Right, denominator over denominator puts it into the numerator. Is everyone okay with the math? This algebra? This is algebra, not chemistry. So. All right, so that puts the seconds up here, so I'm left with natural log of 0.14 minus natural log of 0.88 divided by minus 28, and the final units are seconds. Okay. All right, good. Right, natural log of 0.14 minus natural log of 0.88. Okay, you see that minus and that minus cancels, and divided by 28. So what did you guys get? 0.0656 seconds. So 65.6 milliseconds. Okay, so this is the answer I'm getting. Just check my my calculator with yours. Try to solve it right. I don't know. Did I solve this right? Okay, let me do this again. Natural log 0.14. Minus natural log of 0.88 divided by 28. Okay, yeah. Okay, 65.6 milliseconds, or 0.0656 seconds. Right. All right, so how long does it take for this substance? How long does it take for this reactant A to go from starting amount 0.88. How long does it take to go down to 0.14? Okay. How long does it take initially? And how long does it take to go to 0.14? Okay. 0.0656 seconds, or 65.6 milliseconds. Okay, after 65.6 milliseconds, this will decay from 0.88 starting to 0.14. Okay, this is according to first order kinetics.
So wait, how do we get from 0.0656 to 65.6 again?
I multiplied by 1,000 to go from seconds to milliseconds.
Okay.
But you can put this on the exam, that's fine. Move on to another problem. Yeah. Another practice problem. Okay, let's go to page 11 here. I'll let you guys read over this. Just some information for you to that I think I went over concerning first order reactions and first order decay. Let's just jump ahead to this practice problem together. We'll do it.
So all the stuff like up there, we kind of already went over and like.
Yeah, just read it to refresh yourself. All right, calculate the half-life of N2O5. Its decomposition has a first-order rate constant of 5.4 times 10 to the minus 4 inverse seconds. Okay, you see that seconds to the minus 1? Okay. So that's just the same thing, rate constant. What is rate constant? That's lowercase k. That's 5.4 times 10 to the minus 4 inverse seconds. Alright, so what is half-life? Time in which how much decays? 50%. Okay, the time in which 50% is gone. Okay, time in which 50% has decayed. And what is the order of decay for this? Okay, so what equation will we use, Antoinette? Okay, the first order half-life. So what equation can we use? Okay. Let's go back to our rate sheet here. What equation are we going to use? It's first order. Half-life is 0.693 divided by k. So this is straight up plug and chug. Alright, so that's what I'd like for you to do on the test. Alright, so the half-life here is going to be divided by k. Alright, so 0.693 divided by 5.4 times 10 to the minus 4 inverse seconds. That is, okay, the seconds in the denominator of a denominator goes straight up to the numerator. Yes, so what's 0.693 divided by 0.00054? What did you guys get? 1283 seconds. Got that? Perfect, thank you. All I need is one person to make sure I did the calculator right. Okay, 1,283 seconds. Actually, if you take this and divide it by, you don't have to do this on the test. Okay, but if you divide it by 60, 1 minute is 60 seconds. You get it in minutes. So about 21.4 minutes. Okay, in 21 minutes, this is 50% gone. Okay, first order. This is the equation. We plug and chug it, and this is what we get. Plug and play. Okay. All right, shall we move on to our next problem here? Yes? page 12. All right, this one is second order. All right, second order. So the reaction 2A goes to B is second order with the rate constant 51 m to the minus 1 minutes to the minus 1 molar minus 1 minutes minus 1 at 24 degrees. So just want to reiterate to you guys that this is the same thing as 51. We can take the m down, molar down, and we can take the minutes down, okay, into the denominator. And it's second order, starting with initial concentration 0.0092. How long will it take for T? How long? What is how long? Time for it take to get to 3.7 times 10 to the minus 3, which is also 0.0037 molar. All right, so what equation shall we use? Let's go back. Okay. Will we use zero order, first order, or second order? Okay, what equation? Okay, so this is the equation that we're going to use. All right, so let's write it out, plug it in, chug it out, get the answer. And then we'll move on to part B. So 1 over A at some time t is going to equal to 1 over the initial concentration of A naught, plus KT. Okay, so we got to solve for K. We got to solve for T time here. Okay, so what's over 1? What is 1 over AT? 1 divided by 0.0037 molar. Okay, what is 1 over A naught? 0.0092 molar. Okay, plus K. What is K? 51. Okay, M at the bottom, minutes at the bottom. And T is what we're trying to solve for. All right, can we solve for T here? Over 0.0037 m minus 1 divided by 0.0092 m equals 51 divided by m times minutes times t. Okay, everyone okay with this math? 1 over that, I move this to the other side. 1 over 0.0037 minus 1 over 0.0092. What is this on our calculator? Can someone calculate this with me? Yeah. I'm getting 161.575 divided by m minus 51 divided by m molar times minutes. Okay, times t. Alright, are you guys getting that? Did you get this? 1 over this minus 1 over that equals this. Equals 51 over m time molar times minutes. Alright, I'm going to cross multiply to solve for t. Okay, let's cross multiply to solve for t. And this will be 161.575 m times minutes divided by 51 m. Okay, and this is going to equal to t. This is just math now. All right, cross multiply this. This leaves t alone on the other side. This leaves t time t alone on the other side. All right, the capital M cancels. We're left with minutes. So 161.575 divided by 51. We're left with minutes, and it's about 3.17 minutes. Yes. All right, thank you. 3.17 minutes. Okay, so this is our answer. After 3.17 minutes, this will go down from decay from initially 0.0092 to 0.037. After 3.17 minutes, this will go down from 0.0092 to 0.0037. All right, let's finish up part B now. Calculate the half-life of the reaction. Okay, so the half-life. What is the equation for the half-life? And what order is this? Second order. So we are going to use this equation, 1 over Ka naught, initial concentration A naught. All right, so let's go ahead and do that. Okay, so K is this 51. That's K. What is the initial concentration of A? Okay, so the M's cancel. Okay, this minutes in the denominator of a denominator goes up to the numerator. And we are left with just okay, the minutes stay here in the numerator. Remember, half-life is a time. Half-life is a time. So what's 1 divided by 51 times 0.0092? .13 minutes. Got it? 2.13 minutes, okay. So this is the half-life. So let me ask you guys this question. I'll ask this to you, Antoinette. Okay? I'll pick on you, okay? After 2.13 minutes, how long will this, what will the concentration of this be? It's the half-life. Half-life. So after 2.13 minutes, what will be the concentration of A? The concentration of A will be its half-life. So what do you need to do? It'll be 1/2. Okay? So what will half of 0.0092 be? Point 0.0046. 0.0046. Okay. Why is it after 2.13 minutes this will go down by half? Why is that? Because what did we just calculate?
Time.
Time, but what specific time did we calculate? You're right, the time. But what time is this called?
The half-life.
Half-life time, yes. Okay, the half-life time. Okay, any questions?
So the original half-life time for like the original one, like for the K equals 51 over M.
That's the rate constant.
Oh, the rate constant. Oh, okay. Yeah, I don't think I caught like the last part, like the original, like the first part, the last part.
So after 3.17 minutes, this will go from 0.0092 to 0.0037, and after 2.13 minutes, which is the half-life, it's going to go down by 1/2.
All right, thank you.
Yeah, thank you. Okay. Yes, ma'am.
Divided the original concentration by the time of the calculator.
Yes, because what is the definition of the half-life, Maria? And yes, so the time in which 50% has decayed. So the time in which 50% has decayed, we divide it by 2. Okay. So after 2.13 minutes, this has gone down by 50%. Well, what's 50% of 0.0092? It's 0.0046, okay? All right, shall we do a zero order reaction now? We did a first order, we did second order. Now let's do a zero order reaction. And then I think what we'll do is we'll do a, let me see, let me just give you how much time do we have here? About 20 minutes. Let's see if we can do we'll stop at page 16. Stop at page 16, and then on Thursday we'll finish up chapter. Yeah, we'll stop at page 16. Okay. All right. So we'll do a zero order reaction now. Okay, if a zero order reaction, okay, so again, like before, Bailey and everyone else, you can just read this to refresh your memory on this. Okay. We'll just go ahead and jump into the problem. If a zero order reaction takes 100 minutes for 50% completion, how much time, okay, we got a time here. How much time will it take for 75% completion? Okay. So it's a zero order. So what equation shall we use for zero order? All right. So what is the half-life actually for this? What's the half-life?
50 minutes?
That's not 50 minutes.
No, that is half. My bad. No, I thought that was original time. My bad.
So what's the half-life? 100 minutes. Okay. Very good. You don't overcomplicate things, Bailey. All right. The half-life here is 100 minutes because it's literally 50% completion. So let's go ahead for a zero order reaction. The half-life is this equation. Okay? So I'm going to use this equation and solve for K. Okay, rate constant K. All right, so they don't give me an initial concentration here. Okay, but I'm going to call, because remember, this is a decay, right? This is a decay. So what's a concentration that I could have? Okay, I'm going to call that, the starting material, I'll call 100% or 1. 1. Okay? So I'm going to make A naught 1. And T1 half is 100 minutes. It's 2 times K, okay? I'm going to make my initial concentration 1 molar. You can make it anything, okay, but 1 is an easy number. Okay, I could make your test 150%, but that makes it hard for me to, too much math. 100%, okay? Then everyone is, either you got 75%, 60%, 50%, okay? So I'm just going to make things 1. Okay, so make our initial constant.
initial.
Yes, sorry.
Initial 1 m.
Okay, molar. Okay, you can make anything. I'm just going to make it 1, okay, because it's easier. All right, so here we'll solve for a rate constant K. $100 minutes times 2K over 1M. So K is going to equal to 1M divided by 200 minutes. Just made the initial concentration 1 molar divided by 2K. Half-life, as you guys mentioned, you calculated it as 100 minutes. Okay, this is the definition, the very definition of half-life. All right, so what's 1 divided by 200? I can do that on my calculator. It's 0.005. 0.005. Do that here. Yep, 0.005. Okay, so from my half-life, I was able to calculate K. Okay, so we want initial concentration is 1, and then how much time will it take for 75% completion? I'll call that 0.75 m. Okay, I'll call that 0.75 m. All right, so now let's use this equation here for 0 order. Okay, concentration of A equals A naught minus KT. A naught minus KT. Let's see here for a second. All right, so this is going to be 0.75 molar. Okay, initially I just made it 1 molar, just for easiness, okay? Just to make things easy for us. Minus K, which we already solved for here, 0.005 m to the minutes, okay, times T. Okay, so we have to solve for T. This will give us the time it will take to go to 75% completion. The time it gets to 50% completion, starting with 1, is 100 minutes. All right, so 0.75 big M minus 1 big M equals to minus 0.005 m divided by minutes times T. Right, 0.75 m minus 1 m is minus 0.25 big M, molar, moles over liter. Equals minus 0.005 m divided by minutes times T. Okay, I'm going to cross multiply again, just like the last problem. Let's cross multiply to get us the time T. The big M and big M cancels, the minus and minus cancels, so minus 0.25 divided by minus, so you know the minus is canceled, so 0.25 divided by 0.005, 50 minutes. Is that what you guys got? 50 minutes? And this is our answer, 50 minutes. Okay?
So I even guessed like what the answer was for that before we did anything.
Oh, you guessed it?
No, yeah, remember when I said the 100 minutes, I said 50 minutes instead of 100?
Oh, that was the answer? You gave the answer
I
out?
thought that
Wow.
was funny. I didn't even know. We didn't even do any alpha.
Oh, maybe you did some ratios in your head? I don't know. Okay. Good job. All right, so we calculated K for the zero order, and then we plugged in that in here, and we got the time in which this will go from 1 molar, I said 1 molar, I started it at 1 molar to 0.75 molar. If it gets 100 minutes to get to 50% completion, take an additional 50 minutes, it will be 75% completion. Okay. Okay, so the actual answer here is not 50 minutes. So what's the actual answer? If it takes 100 minutes to go to 50%, how long will it take to go to 75%? What's the actual answer? It's not 50 minutes, but what's the answer? 100 minutes to go to 50%, okay, and then 50 minutes to go to 75%. So what's the answer? It'd be 150 minutes, okay, to go to 0.75 molar. Okay, 100 minutes to go to 50%. Add another 50 minutes to go to 75%. So the answer is 150 minutes, okay, to get to 0.75 molar. Okay. So this is our answer. Okay, it takes 100. Let me just draw it out here. Concentration over time. Okay, so this we know is 150%. So it's 75% completion. Oh, actually, 50% completion, 75% completion. Yeah, it's 150 minutes. Yeah. 75% completion. Completion. So, yeah. Anyways, don't worry about this. 50% takes 100 minutes. To go to 75% completion, it's going to take 150 minutes. All right, so let's, what's the page is that? Page 13. All right, let's just quickly go over page 14, 15, and then I'll stop you guys at page 16. All right, so 2 more pages to go. All right, so this is a summary of all of our equations, so make sure you have access to these for the exam. Okay, 0, first and second order. All right, so now let me tell you something about activation energy. All right, so totally different topic here, activation energy. Activation energy is EA. Okay, EA, activation energy. This is a hump. Okay, this is a hump. Right, so let me explain it to you this way. How many of you have ever sat, or I don't know, maybe maybe you're too young to have toddlers or have a cousin, nephew, niece who's a toddler? No kids around you?
No, I'm 18, so.
Okay, do you have a
No,
niece
no.
or a nephew?
No, literally, like my youngest like cousin is literally 17, and I have no siblings, so.
You remember when he was? How many of you remember we have a 2-year-old or a 3-year-old? Okay, you remember that? Okay, have you ever tried putting a sweater on them? And what's that situation like? Not good? All right, so let me try to draw this in terms of energy. Okay. All right, so here's the kid. And you have to put this sweater on him because, you know, it's going to be ice tomorrow. Okay, so Mackenzie, maybe Maria, is this easy, you said? Okay, why is it not so easy? Okay, because they squirm. Okay, squirmies. Okay, so you put it on, you have some trouble, you put a lot of energy, you put a lot of energy, they squirm, okay, they put a lot of energy, you put a lot of energy, up to a point here where you just got them, you got their head just in their collar, and you got their arms almost here. Let's see if I can. Okay. You almost got it, and then bam. Okay. All you got to do is pop the head out, stick this arm out. Okay. They usually do that on their own. And now you have a swarmy kid with a sweater on this time. Okay? So this stage, to get to this point here where you expend all this energy just to get to the state where it's at that moment, right at that moment where you can easily put the sweater on, okay, put the arms out, put the head out of the collar, okay, but you had to go through, I don't know, what's the word? You have to go through some energy, okay? So this point right here, this hump, is called the activation energy. Okay, it's the amount of effort you have to put in. And then after you put in that effort, how is it after a certain amount of effort? It goes downhill from there. Okay? So the uphill climb, the uphill ascent to the point where you have to expend all of this energy, that's called the activation energy. All right, and for a reaction, the activation energy is the hump. Okay, so we have reactants that come together. Okay, but it's not like, oh, a reaction. Okay, the reaction has to have two things for it to happen. One is they have to have the right orientation, and they have to have the right collision frequency. Okay?
So what's the thing that we should really take away from that thing exactly?
What we should take away from this exactly is that for a reaction, the molecules must have the right orientation and right collision frequency. For that to happen, it needs to get to a certain energetic state. It needs to get over the hump, and that hump is the activation energy. Just like you guys that babysat or have nieces and nephews or toddlers, you have to get over the hump to put the sweater on. Okay, up to a certain point, it becomes easier. It gets, in your words, all downhill from here. Okay? But to get all the way to that point, that's called the activation energy. Okay, up to that point, once you get to the stage where they're just about ready to put the sweater on, it's all downhill from here. For a reaction, if the molecules have the right orientation, okay, and they collide with the right frequency, to get to that state, that's called the activation energy. So it's not like this. Okay, it maybe is like this. Okay, it's not like this, slow, slow, slow. Okay, it's got to be bam. Okay, not this, because that's the wrong orientation. Okay, that's the wrong three-dimensional orientation. All right, so these two factors must happen. Okay, to put on a sweater, okay, you need the kid to be, I guess, the right orientation. Okay, you don't want to put his head in the sleeve. Okay, and I guess he needs to be in the right, you can't be running around all day. Okay, or you can't be chasing him around. Okay, so molecules need the right orientation. Okay, so this is the right orientation for the reactants, not this. And this is the right speed for the reaction. Okay, not this. Okay, so to achieve this, or not this, or not this, okay, you need the activation energy. Okay, once you get to this state, that's called a transition state, where everything is really downhill. Okay, the state where products emerge. All right, so my final thing here before we go is that this is what it will look like. Okay, a profile for a reaction. Okay. Right, so analyzing this, there's one thing here. This hump is called the activation energy. Okay, you need the right collision frequency and right three-dimensional orientation. Okay, these are the reactants. Okay, these are the products.
Oh, okay, so from a hump, so from an initial starting point all the way to like the hump, that's what the activation energy is.
Right.
Okay.
Right collision frequency and right orientation. And sometimes, some cases, the products release energy. They release heat to the surroundings. So we call that an exothermic reaction. Okay, this is heat that's released to the outside, to the surroundings. Heat released. Okay, and it's usually released to the outside. Right, we want to contrast that with an endothermic reaction. You still have the same activation energy. Okay, you still have that same transition state where right at that moment products will happen. You still have that transition state. Okay, you still have to overcome the hump. We will call that hump the transition state. But as you said, it all goes downhill from here. Same thing, but this time when you have products, sometimes you need some energy. Okay, so this would be what we're going to call an endothermic reaction. So this may be heat released to the surroundings. This is heat required from the surroundings. Okay, so that's the difference between an endothermic and exothermic reaction. Okay, it depends where the products are in terms of energy. But for us, remember this activation energy EA is the hump. Okay, consider putting a sweater on a small child. How is that possible? You need to put in a lot of energy. The energy you have to put in is the activation energy. After that, putting on the sweater becomes easy for the child. Okay, so I will see you all on Thursday, hopefully, and maybe for the I think the lab also, if you didn't come Monday. Right.
So the one thing you really get like maybe 15 and 16 are these diagrams, correct? That would.
Yes, these diagrams you should know. Okay.
Okay.